Have you ever wondered what might happen if we combine AI and quantum computers? Would this combination destroy our planet or enhance our understanding of the universe? As technology progresses, we are eagerly awaiting the arrival of quantum computers. Scientists are working tirelessly to develop these advanced machines. However, there has been a recent development where the US government has pressured Google and NASA to shut down their quantum computer development efforts after something terrifying happened.
And also where Google met the challenge. They beat a standard supercomputer at a certain select question. So in other words, we have already achieved quantum supremacy. That is, quantum computers on select problems can exceed the capability of any digital computer.
If someone asked you to picture a quantum computer, what would you see in your mind? Maybe you see a normal computer just bigger, with some mysterious physics magic going on inside? Forget laptops or desktops. Forget computer server farms. A quantum computer is fundamentally different in both the way it looks and, more importantly, in the way it processes information. There are currently several ways to build a quantum computer, but let's start by describing one of the leading designs to help explain how it works. Imagine a light bulb filament hanging upside down, but it's the most complicated light you've ever seen. Instead of one slender twist of wire, it has organized silvery swarms of them, neatly braided around a core. They are arranged in layers that narrow as you move down. Golden plates separate the structure into sections. The outer part of this vessel is called the chandelier. It's a supercharged refrigerator that uses a special liquefied helium mix to cool the computer's quantum chip down to near absolute zero. That's the coldest temperature theoretically possible. At such low temperatures, the tiny superconducting circuits in the chip take on their quantum properties. And it's those properties, as we'll soon see, that could be harnessed to perform computational tasks that would be practically impossible on a classical computer. Traditional computer processors work in binary. The billions of transistors that handle information on your laptop or smartphone are either on, 1, or they're off, 0. Using a series of circuits, called gates, computers perform logical operations based on the state of those switches. Classical computers are designed to follow specific inflexible rules. This makes them extremely reliable, but it also makes them ill-suited for solving certain kinds of problems, in particular, problems where you're trying to find a needle in a haystack. This is where quantum computers shine. If you think of a computer solving a problem as a mouse running through a maze, a classical computer finds its way through by trying every path until it reaches the end. What if, instead of solving the maze through trial and error, you could consider all possible routes simultaneously? Quantum computers do this by substituting the binary bits of classical computing with something called qubits. Qubits operate according to the mysterious laws of quantum mechanics, the theory that physics works differently at the atomic and subatomic scale. The classic way to demonstrate quantum mechanics is by shining a light through a barrier with two slits. Some light goes through the top slit, some the bottom, and the light waves knock into each other to create an interference pattern. But now dim the light until you're firing individual photons one by one, elementary particles that comprise light. Logically, each photon has to travel through a single slit, and they've got nothing to interfere with. But somehow, you still end up with an interference pattern. Here's what happens according to quantum mechanics. Until you detect them on the screen, each photon exists in a state called superposition. It's as though it's traveling all possible paths at once. That is, until the superposition state collapses under observation to reveal a single point on the screen. Qubits use this ability to do very efficient calculations. For the maze example, the superposition state would contain all the possible routes. And then you'd have to collapse the state of superposition to reveal the likeliest path to the cheese. Just like you add more transistors to extend the capabilities of your classical computer, you add more qubits to create a more powerful quantum computer. Thanks to a quantum mechanical property called entanglement, scientists can push multiple qubits into the same state, even if the qubits aren't in contact with each other. And while individual qubits exist in a superposition of two states, this increases exponentially as you entangle more qubits with each other. So, a 2-qubit system stores 4 possible values, a 20-qubit system more than 1,000,000. So, what does that mean for computing power? It helps to think about applying quantum computing to a real-world problem, the one of prime numbers. A prime number is a natural number greater than 1 that can only be divided evenly by itself or 1. While it's easy to multiply small numbers into giant ones, it's much harder to go the reverse direction. You can't just look at a number and tell its factors. This is the basis for one of the most popular forms of data encryption called RSA. You can only decrypt RSA security by factoring the product of two prime numbers. Each prime factor is typically hundreds of digits long, and they serve as unique keys to a problem that's effectively unsolvable without knowing the answers in advance. In 1995, MIT mathematician Peter Shor, then at AT&T Bell Laboratories, devised a novel algorithm for factoring prime numbers whatever the size. One day, a quantum computer could use its computational power and Shor's algorithm to hack everything from your bank records to your personal files. In 2001, IBM made a quantum computer with 7 qubits to demonstrate Shor's algorithm. For qubits, they used atomic nuclei, which have 2 different spin states that can be controlled through radio frequency pulses. This wasn't a great way to make a quantum computer because it's very hard to scale up, but it did manage to run Shor's algorithm and factor 15 into 3 and 5. Hardly an impressive calculation, but still a major achievement in simply proving the algorithm works in practice. Even now, experts are still trying to get quantum computers to work well enough to best classical supercomputer. That remains extremely challenging, mostly because quantum states are fragile. It's hard to completely stop qubits from interacting with their outside environment, even with precise lasers in supercooled or vacuum chambers. Any noise in the system leads to a state called decoherence, where superposition breaks down and the computer loses information. A small amount of error is natural in quantum computing because we're dealing in probabilities rather than the strict rules of binary. But decoherence often introduces so much noise that it obscures the result. When one qubit goes into a state of decoherence, the entanglement that enables the entire system breaks down. So how do you fix this? The answer is called error correction, and it can happen in a few ways. Error correction number 1. A fully error-corrected quantum computer could handle common errors like bit flips, where a qubit suddenly changes to the wrong state. To do this, you would need to build a quantum computer with a few so-called logical qubits that actually do the math and a bunch of standard qubits that correct for errors. It would take a lot of error-correcting qubits, maybe 100 or so per logical qubit, to make the system work. But the end result would be an extremely reliable and generally useful quantum computer. Error correction number 2. Other experts are trying to find clever ways to see through the noise generated by different errors. They are trying to build what they call noisy intermediate-scale quantum computer using another set of algorithms. That may work in some cases, but probably not across the board. Error correction number 3. Another tactic is to find a new qubit source that isn't as susceptible to noise, such as topological particles, that are better at retaining information. But some of these exotic particles or quasi-particles are purely hypothetical, so this technology could be years or decades off. Because of these difficulties, quantum computing has advanced slowly, though there have been some significant achievements. In 2019, Google used a 54-qubit quantum computer named Sycamore to do an incredibly complex, if useless, simulation in under 4 minutes, running a quantum random number generator 1,000,000 times to sample the likelihood of different results. Sycamore works very differently from the quantum computer that IBM built to demonstrate Shor's algorithm. Sycamore takes superconducting circuits and cools them to such low temperatures that the electrical current starts to behave like a quantum mechanical system. At present, this is one of the leading methods for building a quantum computer, alongside trapping ions in electric fields, where different energy levels similarly represent different qubit states. Sycamore was a major breakthrough, though many engineers disagree exactly how major. Google said it was the first demonstration of so-called quantum advantage, achieving a task that would have been impossible for a classical computer. It said the world's best supercomputer would have needed 10,000 years to do the same task. IBM has disputed that claim. At least for now, serious quantum computers are a way off. But with billions of dollars of investment from governments and the world's biggest companies, the race for quantum computing capabilities is well underway. The real question is, how will quantum computing change what a computer actually means to us? How will it change how our electronically connected world works? Impact of quantum computing on artificial intelligence. Data can be processed faster by quantum computers than by conventional computers. In other words, AI systems will be able to learn and improve faster. If quantum entanglement is utilized, algorithms may also be able to exploit correlations between variables more easily. Quantum computers can handle complex optimization problems that traditional computers cannot handle, making AI algorithms run better. This could lead to artificial intelligence that is more powerful and intelligent than anything we have ever seen, since quantum computing does not follow classical physics laws. Many AI applications, such as planning and scheduling, can benefit from quantum computing because it helps explore viable solutions to problems. AI architectures can be developed more efficiently and at a larger scale using quantum computers. There are certain calculations that quantum computers can perform that traditional computers cannot solve, leading to the development of new AI algorithms. For example, Shor's algorithm can be used to factor large numbers, and quantum computers can simulate quantum systems more efficiently than classical computers. By using quantum annealing, problems that cannot be solved classically can be solved using quantum computers. The use of quantum computers can verify the results of AI algorithms to ensure that they are correct and error-free. In quantum computers, AI systems can learn faster and be better prepared for real-world situations by creating powerful simulation environments. Quantum computers, for example, do not forget things catastrophically like classical neural networks do. Because of this, they are better at lifelong learning since they can learn new things without forgetting how to do old things. AI systems can use quantum computers to protect sensitive data. Moreover, parallel processing can be used to counter cybercrime. Unlike classical computers, which exist in only one state, quantum computers can be in multiple states at once, allowing them to find better algorithms. In this era of growing data volumes, companies are no longer limited by traditional computer technologies to analyze complex scenarios. These businesses require sophisticated models that can analyze all types of scenarios. It is estimated that by 2025, the healthcare industry's data generation will grow at a compound annual rate of 36%, which is 6% faster than manufacturing, financial services, logistics, and e-commerce. By using quantum technology to develop better models, we may be able to treat illnesses more effectively, reduce the risk of financial collapse, and improve coordination. Quantum computers have demonstrated success in accelerating DNA sequencing in the medical field and accurately predicting traffic volumes in transportation. Quantum computing is expected to play a crucial role in advancing our understanding of biology and evolution, enabling more effective treatments for diseases such as cancer, and even aiding in mitigating the effects of climate change. Every day, we generate approximately 2.5 exabytes of data. Ordinary CPUs and GPUs are unable to handle such a large amount of data, whereas quantum computers are designed to quickly identify patterns and anomalies based on this massive amount of data. As quantum computing and artificial intelligence are applied to the banking and financial industries, fraud detection will be improved and enhanced. In addition to the ability to recognize patterns difficult to detect with traditional equipment, models trained on quantum computers would also be able to handle the large amount of data that these machines could handle. Advancements in algorithms would assist in achieving this goal as well. The potential applications of quantum computing in various fields are rapidly gaining traction. However, there has been little discussion about how this technology will impact artificial intelligence in the future. Quantum computers can solve decoding problems much faster than classical computers, and they can also model large-scale systems and molecules. As quantum computing becomes more accessible, it will play a crucial role in the development of artificial intelligence and future applications.